Today we're going to start with trigonometric ratios. Trigonometric, trig meaning triangle, and nometric meaning measure. We're going to measure triangles. We're going to look specifically at the ratios of triangles, specifically right triangles. We've been playing around with special triangles, 45, 45, 90, and 30, 60, 90. We're going to now look at triangles that have all different types of angles. This is a little bit of math humor. The question was find x, and the student wrote here it is, instead of figuring out that it was actually 5 centimeters. So before we do that, let's do a little bit of review. Go ahead and work out these problems. I will go ahead and pause the video, work out these problems, and then I will reveal answers for you. A little quick review of geometric means and Pythagorean theorem. Okay, so go ahead and work these out and then compare to what I reveal. Okay, hopefully you found these answers. If not, you should pause, go back, and figure out where you made your mistake and review these concepts. But we're going to move on. Okay, so I want to start by thinking a little bit about similar triangles. So for example, if we start with a 45, 45, 90 triangle, and we're going to have the sides, the lengths be 1 for the leg and then radical 2 for the hypotenuse. Hopefully you remember that to get the length of the hypotenuse, you take the length of the leg and you square it by, you multiply it by radical 2. Sorry, this slide is not in your notes, so you're just going to have to add it to your notes. It's mostly to help you think about what's happening, so you don't even have to take notes, just pay attention, I guess. Alright, now if I take that triangle and I blow it up and I make it bigger, like this, then hopefully you see that we have two similar triangles. Notice that the angles are all congruent, or the corresponding angles are congruent, and that the sides are proportional. So instead of going 1, 1 radical 2, we go 2, 2 radical 2. Now what we're going to do is take a look at some of the ratios involved with these triangles. Specifically, let's take a look at the ratio of the leg to the hypotenuse. In the case of the triangle on the left, the leg is length 1, the hypotenuse is radical 2. We rationalize the denominator, multiplying top and bottom by radical 2, and we get radical 2 over 2. So that would represent the ratio of the leg to the hypotenuse for this 45, 45, 90 triangle. Now if I do the same thing with my larger triangle, I should check out the ratio, 2 over 2 radical 2. And what you realize is that the 2's cancel and you get the same ratio as you had before. And that's a really important concept. When you have similar triangles, okay, so any 45, 45, 90 triangle is similar to any other 45, 45, 90 triangle. When you have similar triangles, the ratios of the length to the hypotenuse is identical regardless of the size of the triangle. So those ratios are something we're going to study here today in the next couple days. Let's take a look at a 30, 60, 90 triangle. So here's your 30, 60, 90. Again, just to review, the lengths of the sides, if I call the short side 1, then the hypotenuse would be 2, and then the long leg would be 1 times radical 3, or just radical 3. Now if I take that same triangle and I blow it up really big, and it's still a 30, 60, 90 triangle, but I call the length of the sides 2 and 4 for the hypotenuse, then the long leg is 2 radical 3. Now let's look at those ratios again, except we're going to look at different ratios because this one is not as symmetric. We have a 30 and a 60 and a 90. So let's take a look at a ratio of the short leg to the long leg. And we'll start with the little triangle. When I start with the little triangle, short leg to long leg, I get 1 on the short leg and radical 3 on the long leg. I rationalize the denominator and I get, I'm not going to rationalize it yet. I'm going to compare that to the ratio for the other triangle, which is short leg to long leg, 2 over 2 radical 3. And hopefully you realize that those two results are exactly the same. And if you rationalize the denominator, you're going to get radical 3 over 3. So that ratio of the side to the long leg, the short side to the long leg, is going to be exactly the same whether the triangles are big or small. So that's going to be true for all 30, 60, 90 triangles. If I look at the long leg ratio to the hypotenuse, okay, long leg to the hypotenuse, that's going to be 2 radical 3 over 4 for the big triangle, and radical 3 over 2 for the little triangle. hopefully you see that those are exactly the same, which reduces to radical 3 over 2. And by the same token, the short side to the hypotenuse, that ratio becomes 1/2. Okay? So, what we're learning here, is we're looking at specifically at these special triangles, is if you take two triangles and they are similar, then the ratios of those relationships of the lengths of the sides are equivalent for any size triangle. Okay, I'm going to skip ahead here. I got these remnants, I got to get rid of them. All right, there we go. And here are the definitions of these ratios that we're talking about. So we're going to talk about 3 different ratios to start. Okay, the first one we call the tangent, tangent theta, so theta being the angle, and we abbreviate by saying tan. Then we have sine, S-I-N-E, which we abbreviate with S-I-N, and then cosine, which we abbreviate C-O-S. So as often we'll just say tan, sine, cos. Okay? Now, it turns out that the tangent is defined as the ratio of in a right triangle of an opposite side over an adjacent side. So if this is your angle right here, whoops, sorry, come back. If this is your angle right here, then the opposite side is the side opposite the angle. The adjacent side is the side that is included with the angle but is not the longest side, okay? Because the hypotenuse gets to be the longest side. So you first look at any right triangle and you're talking about a certain angle, you want to identify what's opposite, what's adjacent, what's hypotenuse, okay? So tangent is defined as the tangent of an angle is equal to the opposite over the adjacent. The sine of an angle is defined as the opposite divided by the hypotenuse. Okay, so sine of an angle is the ratio of the opposite side over the hypotenuse. And finally, the cosine is the adjacent over the hypotenuse. Okay, so that's how we're going to define these ratios. So tangent, sine, cosine. Now, a little way that we all tend to remember this is we say SOHCAHTOA. Okay, so sine is opposite over hypotenuse. Okay, cosine is adjacent over hypotenuse. Tangent, opposite over adjacent. So S-O-H, opposite over hypotenuse. Cosine, adjacent hypotenuse, and tangent, TOA. Okay, so soak your toe in a bucket. Okay, SOHCAHTOA. That's how we kind of remember these different trig ratios. So if I'm given a triangle such as this is a nice little Pythagorean triple, so the numbers are going to work out nicely and how many radicals. And I want to know what's the sine of theta. All right, so I look at theta and I say, what's the opposite side? The opposite side is going to be 5. What's the hypotenuse? The hypotenuse is going to be the longest leg, which is 13. And so there it is. The sine of theta is 5/13. And that's it. You're done. Cosine, adjacent over hypotenuse, is, adjacent side is 12, hypotenuse is 13. And then finally tangent. Tangent is the opposite over the adjacent, TOA, okay, opposite over adjacent, so that would be 5/12. And that's it. You've just computed your sines, cosines, and tangent ratios. In this case, we got nice little neat fractions. Okay, so go ahead and fill out the rest of this table. So I'm going to pause, or you should pause the video, and calculate what you can. I'll do the first one for you. So sine of angle A is going to be the opposite over the hypotenuse. So opposite of A is 12. Hypotenuse is 13, so it's going to be 12 over 13. Okay, so I've done the first one. You go ahead and do the rest. Okay, we're back. So here we go with the rest of the results. Check your answers, pause your video, go back if you need to fix anything. So, tangent ratios of any angle between 0 and 90 are going to be constant. So the tangent of 35 degrees is the same regardless of, well, it's the same for any triangle that has a 35-degree angle. That ratio is always going to be the same. And if you want to know the value of tangent of 35 degrees, you could look it up in a table. And this is a picture of a trig table that was published in 1619. The first trig table was apparently compiled back in about 180 or so BC. So these guys have been around for a really long time. People have recognized these ratios are constant for triangles. Here is a table of tangent values. So, for example, if you said the tangent of the angle B is 5/13, like we did in a problem just a moment ago, 5/13, if you plug that into your calculator, you're going to get that is 0.3846. And then you can go and look and see, where do you see 0.3846 on the table? And it looks like it's really close to about 21 degrees. So you would say that the angle that has a tangent of 0.3846 is 21 degrees. And I say approximate because it is not exactly, it's probably 21.0357, something like that. But so B, the angle B, is approximately 21 degrees. So given a ratio, you can find the angle. Or given an angle, you could find the ratio because they're always going to be the same for that particular angle measure. Now try your calculator, okay? Put 0.3846 into your calculator, okay? 0.3846. And now what you're going to do is use your inverse tangent key. In other words, you're going to say, all right, I know this ratio is 0.3846. Well, what angle would give me that? Now you have to make sure your calculator is in degree mode, not radian mode. So talk to me and I'll help you to get yours in if these numbers don't work out, and I can fix it for you. So what you'll do is you'll plug in 0.3846 and then you hit the little button that has a tangent and then it's raised to a little -1 power. So look for that. Sometimes it's in the second level of your calculator right above a tangent button. So not the tan button, but the tan to the -1. If you plug in 0.3846 and hit tan to the -1, you will get 21.037 degrees. Okay, that's still an approximation, but it's a lot closer than we got from the table. So if you're looking for values of these ratios, you can either find them in tables, like the one shown here, or using your scientific calculator. All right, so go ahead with your calculator or a table on page 311 of your text. Go ahead and fill in these values. The sine of 3 degrees, look at the table or use your calculator to figure out what those signs are. I'll do the first one, plug in my 3 degrees and my calculator, and I get 0.0523. So hopefully you find that, okay? Now, go ahead and pause the video and complete your work here. Okay, we're back, and here are the results. Check them, pause, go back if you need to. We're going to keep moving on. All right. Why do we use trigonometry? It's actually incredibly valuable and helpful in solving all kinds of interesting, well, physics problems to be specific, but math problems in general. So they are a tool that we can use to find missing sides of triangles. So for example, let's say you have a building and you measure the shadow of the building, and the shadow of the building is 57 inches from the base of the building because the sun is up here shining somewhere. See, the sun is up here shining somewhere. And so light comes down and you have a shadow, and you know that's 57 inches. And you can use some sort of a protractor type device, or you can eyeball it, and you can figure out that this angle is 55 degrees. Well, just knowing that piece of information, you can now calculate how tall the building is. You don't need to use Pythagorean theorem, but you can, knowing the ratios, calculate what that side's length would be. So I'm just going to show you the answer, but we're going to take you through problems in just a minute, just in case you want to give it a try. So here's how you work it out. I'm going to walk you through how to do these kinds of problems here momentarily. Here we go. So let's say we have this example. You have a triangle. You know it's 56 degrees. You know one side is 32, and you want to figure out the height. Okay? So you take tangent, remember, is tan OA, opposite over adjacent. And opposite of 56 is y, adjacent is 32. So you say y over 32 is equal to the tangent of 56 degrees. Then you go in your little table and you look for the tangent of 56 degrees, and there it is highlighted for you. The tangent of 56 is 1.4826. There's a little boo-boo on the printout there. So 1.4826. And so 1.4826 equals y over 32. Now you solve for y. Multiply both sides by 32, you get 47.4. So we just calculated the height of that building, or the height of this triangle in any case, is 47.4. Here's another example. Let's say you have a road, and you say that it has a grade of 4%. Okay, that's a pretty steep grade actually, for like a railroad would have about a 4% grade. Which means that for every 4 feet you go up, you go out 100 feet. Okay? So the ratio, you got your little right triangle, theta is your angle, opposite of theta is 4. adjacent to theta is 100. Tangent of theta is opposite over adjacent, is 4 over 100, 0.04. So what is that angle? You look over in the table, you look for 0.04 or approximately 0.04, and you find out it's about 2 degrees. You can get more close if you use your calculator, and again, you use your inverse tangent key, that tan to the minus 1. Plug in 0.04, hit that tan to the minus 1. Why don't you try that now? Go ahead with your calculator and see if you can figure out exactly what that angle is, or get closer. Your calculator gets closer than a table will. All right, there it is, 4 100. I get 2.29 degrees. All right, so sine and cosine ratios. Okay, the sine is the opposite over the hypotenuse. Okay, so sine and cosine ratios of any angle are constants. Okay, so the sine of 30 degrees is the opposite over the hypotenuse. In this case, it would be the opposite. Well, you can figure out what, given this triangle, that since the short leg is 8, then the hypotenuse is going to be, then the hypotenuse is going to be 16, right? So you're going to get 8 divided by 16. We'll call that 16, and that's going to be 8 radical 3, okay? The cosine of 30 degrees is going to be adjacent over hypotenuse, which is going to be 8 radical 3 over the hypotenuse, which is 16, which is just going to be radical 3 over 2. Radical 3 over 2. 1/2. That sounds kind of familiar. We saw these exact same ratios just a few minutes ago when we were looking at our similar 30, 60, 90 triangle. It's because the sine of 30 is always 1/2. The cosine of 30 is always the square root of 3 over 2. We have tables of sines and cosines, just like we have tables of tangents. Perfectly valid to look at a table. Nobody really does anymore. We all use calculators. So you have your sine of the angle and the cosine of the angle. All right, so example problem. Find the value of x and y to the nearest tenth. Okay, find the value of x and y to the nearest tenth. Well, sine of 67 degrees, okay, we're given that angle, is the opposite over the hypotenuse, which is going to be y over 120. We look in our table for 67 degrees and find the sine of the angle is 0.920505. So we plug that in for our sine of 67, and we say that's equal to y over 120. We solve for y. Y is 110.5. Then we're going to do the exact same thing with the cosine of the angle. Okay, cosine is opposite, cosine is adjacent, so that's a little typo there. Let's fix that. It's supposed to be adjacent over hypotenuse. So the cosine of 67 is going to be x over 120. And it turns out in our cosine table that 67 degrees gives us a 0.390731. Plug that in for the cosine, solve for x, 46.9. All right, so now let's try this. Okay, we got x degrees, we have 22 and 40. In this problem, we want to figure out what x is, knowing a couple of sides. So first we had to say, well, what sides do we know? Now the 22 side, that looks like it's the opposite side, and the 40 side looks like the hypotenuse. So the question is, which ratio are we going to use? Which one involves opposite and hypotenuse? Okay, so hopefully you remember it's sine SOHCAHTOA, right? Sine opposite over hypotenuse. So you would write an equation that says the sine of x degrees is the opposite of the hypotenuse, 22 over 40. So the sine of x is 0.55. I can get that from my table, or I could get that from, I get that from the calculator, and then from the table I look for 0.55 and find out that it is 33 degrees. So there it is. Okay, so I've just found that angle, knowing two sides. All right, so what we're going to do now, this is some practice. I'll do the first one with you, and then you need to finish. Okay, so use the scientific calculator or the tables to the next, find all the values, the correct lengths. Okay, so I want to find x. X is opposite 38. 46 is adjacent to 38. It's not a hypotenuse. So I'm going to use tangent. Tangent is the opposite over the adjacent, x over 46. So I'll write tan of 38 degrees is opposite x over 46. Oops, getting ahead of myself. Opposite over 46. So if x is 46 times the tan of 38, then I can solve for x and get x is approximately 36. Okay, so go ahead and work the rest of these problems, and then check your work when I'm done. And here we go. All right, good luck with trig.